So our last problem in chapter 10 is really great because it kind of sums up everything that we've been thinking about so far in terms of putting lots of pieces of information together here. So what we have here is the concept that we've already talked about having polar bonds. And so we're going to think about whether or not bonds are polar in a molecule. And then we're going to have to think about the shape of that to think about whether that electronic tug of war is such that it really creates a molecular polarity, or maybe it's such that it cancels things out. So again, we talked about this quite a bit in lecture, but again, this is so important because ultimately at the end of the day, molecular polarity is really what has a lot to do with physical properties and chemical reactivity that we'll see. So you've got three examples to kind of run through here. And again, we assume that we're fairly proficient with Lewis structures so that we can very quickly get to a molecular shape and then apply our new information here. So, ammonia, Lewis structure is this. 4 electron groups allows us to think about the fact that this is going to be trigonal pyramidal. So drawing kind of a trigonal pyramidal shape here. Again, this is trigonal pyramidal. We want to draw bond dipoles if they're there. So these nitrogen-hydrogen bonds are absolutely polar because they are different atoms that are not carbon and hydrogen, and they're pulling in this direction. Now again, if we didn't have the molecular shape to think about, we might think that these would be pulling or pushing in this case in equal and opposite directions and really wouldn't be doing anything. But because of this tetrahedral geometry that we get from having 4 electron groups, but really results in a trigonal pyramidal molecular shape because one of those groups happens to be a lone pair of electrons, we have a vector sum, if you will, of all of these individual dipoles that results in a molecular dipole that looks like this. Now that was a mouthful kind of said fairly quickly, so let me just go over that again. The shape of our ammonia molecule is such that each of these dipoles that we have for our individual NH bonds sum up to an overall molecular dipole that's shown here. So we want to think about every single dipole kind of has a magnitude and a direction, not unlike force vectors that maybe you learned about in physics, right? And when you talked about push and pull and force and vectors with physics, if things were pushing or pulling in the opposite direction, they might cancel each other out. So we think about the same thing here with these dipole moments. We can think about them as kind of being vectors that have direction and a magnitude. And we have to think about whether or not they're going to be summing together or whether they're going to be canceling each other out. In this case, they sum together, and the molecular polarity is such that there's going to be negative electron density towards our nitrogen atom and positive that's kind of surrounding these hydrogen atoms. Let's go through another example here. We've got boron trifluoride. Again, drawing a good Lewis structure will get us with this octet deficient atom, that was kind of one of those violators, a molecule that looks like this. So having 3 electron groups will get us to a electronic shape that's trigonal planar. And since all of our electron groups are atoms, that's what our molecular shape is also going to be. So if I draw that kind of correctly here, we're going to have 120-degree bond angles that we have here. Each of these boron fluoride bonds is polar. Again, fluorine being the most electronegative atom that we have. The dipole moment certainly points towards that. And I don't think I've drawn this as an accurate representation of these vectors point in opposite directions, all 120 degrees apart from one another, all the same magnitude because the bonds are the same. So in this case, these dipoles will cancel out. So dipoles cancel, and we have a non-polar molecule. Kind of didn't finish writing that here, but here our dipoles are additive, and that means we have a polar molecule. Our last one here, and I'm actually going to slip in an example first here to do. I want to do carbon dioxide first. I know we did this in class, but here again is the Lewis structure of carbon dioxide. Looking at the central atom, we've got 2 electron groups around that central atom, so that means our shape is linear. Again, we're not going to have lone pairs, but that shape being linear means that the dipole moments that we draw for these carbon-oxygen bonds, which are polar, they're pointing again towards the more electronegative oxygen atom. The direction and magnitude of these are such that they cancel out, and so this is a non-polar molecule. Once we go through this example, this next problem, you'll see why I went through this example first. But we'd like to look at carbon sulfide. Okay, and they tell us that the atom sequence is sulfur, then carbon, then oxygen. Sulfur being kind of an electronic equivalent to oxygen in terms of valence electrons means it bonds similarly. So we're going to see the same type of bonding in this as we did in carbon dioxide. We also have dipoles. Carbon-oxygen bond is polar. Carbon-sulfur bond is polar. But you'll note what I did differently here is the magnitude of this bond is different. So even though we still have 2 electron groups and we still have a linear species, this is now going to be a polar molecule, because when I take the sum of these individual dipole moments, it's such that I have a molecular dipole. These don't cancel one another out, because even though their direction might be such that they want to cancel out, their magnitude is not the same. So another thing to note is we have symmetry with molecules that have polar bonds but are nonpolar as a molecule. When we break that symmetry by putting in another atom, we end up with a polar molecule. Same thing with this example up here. If I replaced one of these fluorines with a chlorine, this would become a polar molecule because the magnitude of that dipole would no longer be the same and it would not cancel out.